Thanks so much. First of all, it's difficult to go to speak after Chris's talk because the ghost commissioning has been fantastic. Chris captured that just beautifully. The range of objects that they observed during commissioning, the incredible success of the commissioning run, and special thanks to everyone at Gemini for extending that run as well, so that they got the 3 good nights at the end of like 8 or 9 horrible ones. So I'm going to try anyway, though, and be a little bit more general, step back from just the commissioning of the instrument and talk about some science. I hope that's what I was invited to talk about. So first of all, thank you again to the organizers for allowing me to speak at this meeting, and especially remotely. We have been using Gemini instruments for some time now, mainly Grace's, waiting for GHOST, and with a great deal of success. So I'd like to cover that and kind of direct you to where we're going with GHOST. I definitely want to acknowledge many of the contributions made by students and colleagues in Victoria and as part of the Pristine collaboration who are named here. And we'll get going. So let me see, does this work? Oh, please work. It worked. Yes. All right. So before anybody can say anything, I'm sure you're all stunned by the JWST pictures, as I am, and I thought I would start with one, because how can you not? So this image from James Webb that came, it was the first one that I think it was President Biden presented 2 weeks ago, is simply stunning. It's showing galaxies at the highest redshifts when you combine imaging and spectroscopy. And James Webb, just like where I'd like to go with talking about the Metal Poor Galaxy, is interested in studying the early universe. So in this picture, in this image, I don't know if you've taken these images and actually zoomed in for yourself, but I recommend doing it because it's super fun. And there's this one galaxy in there that's a lens. So we know it's at high redshift, but I don't think the redshift for it has actually been published. And you can actually see little globular clusters forming in it. So at least that's what we think. So, I just think this is amazing that we're going to be able to study the actual epoch of globular cluster formation. And as we've known for some time, those are not the most metal poor stars. They're old, but they're probably not the oldest stars. And so, what I'm interested in are actually the oldest stars. So this is amazing. And I'm looking forward to seeing where this goes. But in the meantime, we can also still study our Milky Way to try to understand the early conditions in the universe by using metal poor stars. So if you take that simple timeline, Big Bang happens, universe expands, particles are made, reionization happens. After the dark ages, galaxies start to form, and then we're here today. If you look backwards at that, then you're doing galactic archaeology. If we could look at stars that formed earlier and earlier at earlier times, then we ought to be able to study stars that were forming when the galaxy was being built up. We should be able to study stars that formed maybe right after the first generation of stars that were enriched in only metals from that first generation supernovae. And so if we can find really metal poor stars, things that were made of only hydrogen helium, that would be amazing, but we haven't done that yet. But if we can find metal poor stars, we should be looking at very early generations of stars. And that's the idea, is that if we can look at things that have only a few metals, maybe they were enriched in only one or a few supernovae, or only from a few generations, then we can use those little bits of elements to study which supernovae contributed, what was the mass like, what was the chemistry like, what was the distribution of this gas like, and actually start to study not only formation of the Milky Way, but also origins of the elements. And so this is where I'd like to go with my talk, and why it's loosely just called the Metal Poor Galaxy. But before I go there, the summer's been amazing, right? Only last month, there was also the data release number 3 from Gaia, and that presented a bunch of incredible results associated with galactic archaeology. So for one thing, object classifications for 1.59 billion sources, full astrometric solutions for 1.46 billion sources. So that includes positions, parallaxes, and proper motions. Astrophysical parameters for 470 million objects, mainly from BPRP spectra, which is simply amazing. And this one image that I'm showing you is actually only a measly 32 million objects, but looking at an index that is associated with reddening. So that's amazing. And that index is actually based on the RVS, the Gaia RVS spectra. So these spectra have resolution of about 11,000, only around the calcium 2 triplet region. And they were there to provide high precision radial velocities, full stop. Radial velocities were the primary thing in order to have full dynamical phase space for objects. But also these RVS spectra are used for stellar parameters, metallicities, some chemical abundances for 5.6 million stars, which was just published a few weeks ago. And I want to show you this map because it's a little bit odd because it's a metallicity map, but RVS spectra are for the bright objects complete to only about G of 14, which means really they're the objects that are around us still in the solar neighborhood. So this metallicity map only goes to metallicity of minus 0.3, which is odd. But for the bright objects around us, that kind of makes sense. We're mostly looking at the disk here, even just up to solar metallicity. So we're not, this map is hiding the metal poor stars that are available in Gaia. And so just hit, oh, come on. There we go. So if you really, I don't have time to go into this beautiful, beautiful image here from this paper by the Gaia collaboration, but if you separate all of those stars into quadrants, here's the galactic plane. You can go above the plane and below the plane towards the galactic center. Here's R towards the galactic center or away from the galactic center. And you can actually map out stars in the thin disk and thick disk. And the reason I want to put this image up here, though, is simply to point out that Gaia does find stars down to metallicities of about minus 1.5, but not too many below that. And again, to G of 14th or so, metallicity minus 1.5, this seems to be roughly where Gaia is doing well. So one of my collaborators, Elsa Starkenberg, has recently been comparing SDSS metallicities with Gaia metallicities. And again, as you go fainter, so from G of 15 down to 16 to 17, at metallicity about minus 1.5 in SDSS, you can see that Gaia, especially for the fainter magnitudes, will go anywhere from get a metallicity anywhere from minus 4 to about minus 1. So for brighter objects, more metal rich, it's actually doing pretty well. But for the fainter objects and more metal poor, it's very, very large uncertainties and very few stars that are actually very metal poor. So the extremely metal poor ones around minus 3 or lower are the ones that we actually want if we want to study the early universe. From cosmological models, metallicities of minus 3, looks like most of those objects in our galaxy would have formed within, 68% would have formed within about 1 gig a year, maybe a few later. And so if we want to study the early galaxy, we really want to be studying extremely metal poor stars, which are those below metallicities of minus 3. So Gaia is not going to do it. Instead, this is why there's still room for photometric photometric surveys looking for metal poor stars. The one I've been involved with is the Pristine survey, which is happening at the Canada-France-Hawaii telescope, where a narrowband calcium filter around the calcium H and K lines is converted into metallicities when combined with SDSS G and I data. This was the original calibration. In the 5 years since 2017, we're now calibrating with Gaia data, Gaia G, BP, and RP, and also being able to find revealing extremely metal poor stars. So Pristine and Gaia have now been more coupled. And so there are other surveys. There's a new survey coming out, JPAS, which will also go a little bit deeper, I believe. Super exciting that these photometric surveys are so successful in finding extreme metal poor stars. But again, I'll just focus on Pristine since this is the one that I've been more associated with and also relates to Grace's data. So as of June 2022, last month, this was the Pristine survey region of the galactic halo, plus a couple of individual dwarf galaxies and maybe globular clusters, and a few objects, few fields towards the galactic center. So we're really coupled now to Gaia and searching for metal poor stars to do chemodynamic analyses. So I've just hit return. And so at this point, I'd really like to fast forward to data from this, data from Pristine plus Gaia that we've been following up at Gemini with primarily Grace's and soon to be Ghost. So the first significant follow-up that I want to discuss was studying just Grace's spectra of just 2 stars in the core of Triangulum 2. Triangulum 2 at the time, it wasn't clear if it was an ultra-faint dwarf galaxy or globular cluster. So by finding 2 stars that have different metallicities and that also look alpha poor, they really do have the chemical composition and signatures of an ultra-faint dwarf galaxy. I wanted to bring it up today, even though it's a little bit old, because there have been more stars that have been fainter that have been found and analyzed, so that there's an improved velocity dispersion now, which is a little bit lower, 3.4 rather than 5.1 kilometers per second. This implies a mass to light ratio that's several thousand, whether it's 3,000 or 2,000, a lot. Very large dark matter halo. And I want to point this out because in our original, because of the GRACES data, which was observed in this epoch, we were able to see that one of these objects had no radial velocity variation, whereas the other one did. We were able to identify this object as a binary. And just recently, there's been an analysis of the velocity curve of this binary, where they actually can get the period of the binary and look at the impact of a binary on a very small velocity distribution. So the binary has velocity offsets of roughly 25 kilometers per second, and the velocity dispersion is really, really much lower than that. So this really impacts your interpretation of the velocity dispersion, which then affects what you would assume the mass to light ratio of this object is. So this is just a bit of a warning. In this paper, they say this star actually doesn't affect it that much, but I wanted to mention that because we're going to be looking at ultra-faint dwarfs in the next few slides. Oh, please, slides, come on. It hasn't gone forward for me. Come on. Oh, I'm going to risk it. I'm going to press return one more time. I am not getting slides fast forwarding. Sorry, guys. One more try. Yay. Okay. Hopefully it's not going to fast forward much more. Sorry, then what I wanted to talk about was we're very, very fortunate to receive a large program for GRACES follow-up of pristine objects. The first of those papers was published last year as part of Colin Kilty's thesis, where we followed up on several extremely metal poor stars found in pristine. In the gray is the photometric metallicities that we found in pristine. In the red is actually the low resolution spectroscopic metallicities for the same distribution. So you can see that already we're finding that the spectroscopic metallicities are up to about 0.5 dex higher, but still these are all very metal poor stars. This is minus 2.5 here. So we just picked a bunch of the really metal poor ones, followed up with GRACES spectra, found some super interesting objects. These calcium poor ones, that's really odd. These barium-rich ones, that's less odd, but interesting. Some of the objects are in the Gaia Enceladus merger remnant. And then some objects are even in the galactic plane. So extremely metal poor stars, minus 3 stars in the galactic plane. So this is something Federico Sestito has been working on quite a bit to determine whether or not they're just part of the normal spherical halo, or whether or not these could be remnants of accreted dwarf galaxies. And I think Federico will be speaking a little bit more about that shortly. I want to point out one of them is even retrograde. So it's in the plane, but going the opposite direction, which I think is also pretty interesting. But I'll leave the rest of that discussion to Federico. Federico's also been following up with metal poor stars that we've been observing with GRACES in the galactic bulge. So I won't say too much about this because he's going to talk shortly. But the blue dots in here are the ones we have GRACES spectra for. Again, some of them are barium poor. One of them end up being barium rich, which is interesting. But the one that's barium poor is even more interesting since it falls into a region with other ultra-faint dwarfs. Federico, don't worry, I'll stop there. And I just wanted to highlight that one of the things that's people discuss a lot is when you look at a star in the bulge, you don't know if it's just passing through the bulge or if it's actually born and raised and formed in the bulge. And if we're going to study metal poor stars in the bulge, we actually want ones that form there, because a lot of cosmological simulations suggest that that's where the first stars should have formed in our galaxy. So we're interested in following up on those. Federico is going to talk more about this. This plot down here, which is the same as the mean apocentric distances and Zmax values, I think is super interesting, because also when you look towards the galactic bulge, the distances from Gaia are a lot less certain. You can see this in the Corn-Baylor-Jones distribution. It depends on what the potential looks like and how you interpret these. And so I just wanted to point out something Federico did that I thought was fantastic and is buried in the appendix of his paper, is actually try to take the mean distance and then take plus or minus 0.1 kiloparsecs, and look at what the difference in the orbital parameters would be. And I just think this was really lovely in the analysis. So I wanted to highlight that because I'm pretty sure Federico won't in his talk. Moving on, hopefully. Yes, probably the most fun thing that we did was we discovered C19, the remnant of the most metal poor star cluster. Thank you for the 5-minute warning. And again, I also want to thank Gemini and Noir Lab communications team and staff for helping us with this press release, including making this image. There's C19 off to the bottom there. It looks like a disrupted globular cluster that's just merging with our galaxy, or it's in orbit around our galaxy. It was found as part of the Pristine plus Gaia stream finder. So in galactic coordinates, gray is where Pristine is. These are the objects, individual stars that we were finding from the Pristine survey, noted by their metallicities. Down here, this is just taking just which objects are associated together with C19. We followed up C19 with GRACES, these 3 objects with GRACES, other ones with lower resolution spectra, LAMOST, and at the GTC. And basically, we're finding that these objects are incredibly constant in their metallicity, around minus 3.4. So if I show just a couple more slides from that, for C19, we found that the Bayesian distribution on the prior was really small. So the metallicity really, it looks like a globular cluster with a single metallicity. And yet we found no variations in the iron or magnesium lines, but we found strong variations between at least one object in the sodium stellar lines. So we proposed, based on the lack of a metallicity distribution and based on the sodium and magnesium abundances, C19 is a globular cluster, making it the most metal poor globular cluster that has ever been found. So this was super fun. It went very viral, got picked up by a lot of news agencies, and led to a whole bunch of interviews on like TV and radio, including one of the Gemini webinars. I want to highlight now what we're doing and where we're going with GHOST. So the thing that we've been the most interested in as we've been waiting for GHOST is using GRACES to analyze stars in the outskirts of northern ultra-faint dwarfs. For the GHOST LP, we would like to be doing this in the southern ultra-faint dwarfs. And in this case, we're not using Pristine at all. Alan McConaughey determined a Bayesian analysis methodology to use Gaia data with isochrones and CMDs in order to try to determine members of ultra-faint dwarfs, including out to very high galactocentric half-light radii. So with Fletcher Waller, who's a master's student at UVic, we've been determining abundances and finding that all of these objects that we've analyzed so far are actually members of the ultra-faint dwarf galaxies that we've been looking at in the north. And this is interesting because in Tucana 2, for example, there was a Nature paper earlier this year where there was one object found at 9 half-light radii, as well as another one at kind of 2 and 6. And what's so interesting is that if these ultra-faint dwarf galaxies are survivors of the earliest galaxies and formed in very high mass-to-light ratios with extended dark matter halos, then the objects at their cores within the inner 2 half-light radii would have been things that may have continued to undergo star formation and undergo some enrichment, whereas things that are beyond 2 half-light radii almost certainly were part of the first generation of stars that formed in these objects. And if these are the oldest surviving dwarf galaxies from the early universe, and these are the objects that we really do want to study in order to understand the early star formation, chemical evolution as close to the epoch of reionization as possible. So I wanted to mention this because this is exactly what we plan to be doing with GHOST. As everyone has already seen, and especially from Christian's amazing talk, GHOST this is an old image, but relative to lab specs, the GHOST throughput is not too far off that which was expected. I put in here a little block for where GRACE is, where the throughput is not as good and where the wavelength range is tiny compared to what GHOST will be able to do. And I also wanted to put down here from our GHOST LP from Alan's analysis of southern ultra-faint dwarf galaxies, especially as we go to fainter and fainter magnitudes, we have hundreds and hundreds of targets in ultra-faint dwarf galaxies in the south that have never been observed, many of them at very high outer half-light radii. So we're super excited to get started on our LP. And also just to highlight what Christian said, from a paper by Ian Roeder just a few months ago, this is the GRACES spectral region versus the full GHOST spectral region and beyond. And you can just see in this blue spectral region, which is has amongst the highest throughput of any high resolution spectrograph I've yet seen, is where many of the chemical elements lie, especially of the heavy elements that are so important for distinguishing the different supernovae that may have contributed as first stars. So I know I've run out of time. I'm just so grateful to all of you for the opportunity to talk, to Gemini for the commissioning of GRACE, for purchasing and commissioning and choosing GRACE's GHOST, and super, super excited to start working with it for just its straight up abilities as an amazing high resolution spectrograph. So thanks very much.
Thanks so much, Kim. I think we can all get excited about GRACES and GHOST equally, but let's all focus on GHOST anyway. Any questions in the room for this fantastic talk? Anyone? Oh, Janice?
Hi, Kim. Hi, Kim. Wonderful
Hi,
talk.
Janice.
Hi. About C19. So the main argument for it being a remnant globular cluster instead of some old dwarf galaxy is just mainly the homogeneity in the abundances and star formation, presumed star formation history. How watertight is that argument?
Yeah, it's a great, I skipped over the worst controversial part of it. The absolute precision, there's no metallicity dispersion. That's very unusual. We have 8 objects that all have metallicities of about -3.4, plus potentially a few others. And so with no metallicity dispersion at all, that would be very unusual for an ultra-faint dwarf galaxy. But then on top of that, you can see sodium to magnesium, sodium variations. And so sodium variations are also a characteristic signature of globular clusters. Every globular cluster that we've looked at that's a bona fide globular cluster has stars, has first and second generation or stars in it. So you can actually see these sodium variations. But again, I mean, there's other possible variations, aluminum, which we can't observe with GRACES because there are no aluminum absorption lines. But with GHOST, we can. GHOST, the aluminum lines around 3900, which is available to GHOST, we could see, whereas in GRACES, we don't get that spectral region. So there's so many reasons that GHOST is going to be so much better for these analyses. We'll actually get decent, the range of chemical abundances that are needed to confirm their, objects as globular clusters, as dwarf galaxies, or even right down to the mass of a supernova, an explosion energy of a supernova that may have contributed to an individual extremely metal poor star.
Yeah, that would be amazing.
So to answer your question, though, the one thing I didn't say, though, is the velocity dispersion. So the velocity dispersion is the other thing, and the velocity dispersion from our objects is actually much too high. So this has been super exciting because all the theorists have gone crazy enjoying this, assuming that it's a globular cluster that maybe has interacted with the disk in a unique way that has actually caused the dispersion of the velocities to be larger than you would expect for a very cold object, for a very dynamically cold object. There have been several theoretical analyses and even a few papers coming out.
I wasn't aware of the controversy part of it. So, okay.
Thanks for asking then.
Yeah. That's all really cool and lots of stuff to look forward to. Are there other questions? Because I do have another high level question if we have time.
Any online?
Not yet, no.
Go for it.
Right. So you started off your talk by motivating the study as a way to understand the early universe. right? And I guess I wonder how to reconcile this detailed study of abundances in the nearby universe with the kind of metallicities that we get further out, which are the gas nebular metallicities. So how do you bring those two fields together?
Yeah, that's a really good question. There are people that do quasar absorption line studies, damp Lyman alpha studies, and so we can compare abundances to the DLAs, which I think is interesting. But most of the DLAs that I'm familiar with are redshifts of kind of like 2 to 4-ish. I think what probably like quasar absorption line studies would be even better, but there's I don't know that you can convert. Well, you can, but also the specific elements that you see in emission are different from those typically that we find in absorption. Not completely, but the gas phase abundances versus the stellar atmosphere abundances can be quite different for things like oxygen, for example. So I'm not sure I'm answering your question in a good way. There are some elements that overlap and some that don't. The gas phase versus the stellar atmosphere phases historically have been pretty good, but really limited to only, like we can look at radial gradients in our galaxy. You can compare H2 region abundances with some star formation that's happening nearby in hot stars. So I'm thinking of several things around oxygen, CNO, things like that. But I think the elements that we really want and need to constrain supernovae and the supernova explosion energies are really more like the heavy elements, and you'll never, at least my understanding is you'll never get those in the gas phase. So that's my long answer to a very good question. And to be honest, I don't really know what's going to happen with JWST, right? There's like really new discovery space, and it might be that the emission lines that they're looking at now at high redshifts are such that we can put this together with some of our most metal poor stars. Sorry, last thing too, some of those lighter elements change in the history of a star as well. The heavier ones really don't, but CNO cycling mixing can change those lighter elements, which are often typically the ones that we're seeing in the interstellar medium. So
well, thank you,
so that's
Kim.
a long. Janice, what do you think?
About which part?
about bringing together. That was such a good question about bringing together the chemistry that we get from emission line studies at high redshift, like presumably what's going to happen with JWST and has happened with HST.
I mean, we have trouble doing that in the nearby universes. So it was an honest question, so I don't have an answer. Yeah. But I mean, it's just phenomenal. We can go on and on. I should stop. And
well, I'm sorry. I'm really sorry that I'm not here, because it'd be lovely to have this discussion over dinner.
Yeah, I think we're going to have to continue the discussion online just in this interest of time. But that's one of the benefits of having a hybrid, is that we have a great Slack setup. So please jump online and put your questions in there and get the discussion going.
Thank you.
So let's thank Kim again for the fantastic talk.